Welcome to EECS 373. I'm Lance and Sample, and this module is on serial buses, specifically I2C. All right, to orientate us in the course, this is part of section 5, which is all about serial buses, and this particular module is about I2C, sometimes called I2C, the intra-integrated circuit protocol. All right, so if you want to do a little bit more reading, the manual, the family manual for all the STML processors has a section on I2C, section 49. It has all the information you need to get I2C up and running on your chips, registers, modes of operation, interrupts, all those sorts of things. If you need some more background on serial protocols, serial communication in general, this textbook is pretty good, but there's also a lot of information on the web. I encourage you to go look. There's some great YouTube videos from Micron and STMicro, so feel free to look wherever you need to find information here, or come to office hours. I'll teach you there. All right, so what is I2C? Sometimes it's I2C, sometimes it's I2C. It's the intra-integrated circuit communication standard. Now, I don't know, an odd name if you ask me, hard to pronounce, that's why we all call it I2C. I probably spent the first few years working with this and never knew what the acronym stood for. It was originally invented by Philips in the 1980s for television sets. They needed a compact, easy to use, low-cost way to talk back and forth through their TV peripherals, right? So they had a controller, and then they needed to talk to all their chips. So for their own purposes, they invested the money into developing this. Today, it's the de facto two-wire communication interface. Some of the reasons it's so popular is it's slightly cheaper to make this. You need less digital logic. So while each individual chip is very hard to capture how much less that costs, but when you talk about selling hundreds of thousands of chips, small amounts of money add up. Also, it only needs 2 pins, so it's easy to add to a chip if you just want to have more flexibility for your customers. I2C is pretty easy to add, and it's common. Almost any chip manufacturer that makes microcontrollers is going to have it, and lots of peripheral manufacturers use it. In fact, I would say that it's pretty uncommon. I can't think of a microcontroller I've used in the last 10 years that didn't have both I2C and SPI and UART in some fashion. And almost all peripheral devices, either, so say a fan controller or I don't know, a servo or something. Servo's not a bad example, but say fan controller or temperature sensor. Any of those things are a memory module of I2C and SPI, or built in as an option. You can use either one, or they'll sell a variant of that same exact device with slightly different interface. So super common. Kind of interesting. I always think it's interesting to see what are the market forces that kind of drive innovation, because those help you understand what the bottlenecks are. I just thought it was pretty interesting that since 2016, essentially, Philips, which is now owned by NXP, charges no more licensing fees to use it, because they feel that they want to get it out there. Having the standard out there is better. But they still charge to register addresses with them. So there's still a mechanism to gain a little bit of money, and we'll see why the addresses are so important in just a second. Okay, so I2C has two lines. That's it, right? And ground. Don't anybody say I didn't warn you about the ground. But 2 wires for communication. So serial data and serial clock. Okay. Now, you notice there's no chip select, right? How does the controller tell peripheral 1 to talk versus peripheral 2? In SPI, you would use chip select. And UART, you just wouldn't do it. It was just too hard. So how do we do it here? Well, each device has in it, burned into it at manufacturer time, they've hard coded a address in there. So usually 7, 10, 16 bits, almost always it's 7. It's pretty rare not to have an address of 7. And so there you go. Now the manufacturer has defined what the address is. You look up in the data sheet, say, aha, my fan controller has this address. I will go send it when I want to talk to it. This is how I talk to it. All right, this is how I address it and get it to respond to me. Now, one of the challenges that comes up here is that what happens if you have your favorite audio chip or something and you want to be sending out some tones or pulses or something, or a time of flight sensor. This is a real one that happens to some folks in my group. You have a nice time of flight sensor that measures IR pulses back and forth, and you want to make a little touch interface with it, but you want to use lots of them. And if the device manufacturer says that they're all the same address, you can't put multiple devices, peripheral devices, on the same bus because they'll all try to respond. So you say, what's the range value? And then multiple devices try to respond at once, giving you corrupt data. There's ways around it. There's bridges. There's other hardware you can use to get around that. Some manufacturers will allow an external pin to define maybe the lowest bit or the lowest 2 bits. So you could, on your PCB, ground these special pins or set them high, and that will encode the lowest bits, and that's why you could get multiple peripherals on there. But the addressing is a problem. It's a problem if you want to use multiple of the same chip, but it does solve a whole bunch of other problems when it comes to wiring. So again, this is all just a bunch of trade-off. Anyways, big takeaway, these peripherals all have an address. Go look on the data sheet, figure out what it is. Okay. There is one caveat. If you send out address 0, that's a broadcast to everybody. Don't know when, the canonical example of when you'd want to do that, but it's certainly possible, especially maybe they all responded the same way. They were multiple of the same device. You could say, with all their unique addresses, you could turn them all on and say, start recording, for instance, by sending out an address 0. Anyways, small caveat. Speed, now this is your other favorite part. This is the part where most students freak out. There is, inside of here, this is a pull-up or a pull-down. There are open drain inside of there so that they can all share this. So there's a pull-up resistor that pulls that line up, and a drain, open drain, that pulls that line down. And we'll show you why that's actually the preferred method and what the great benefits of that are in a second. But it does mean that the speed of your bus is defined by these pull-up resistors. So there's kind of a low speed mode, a high standard mode, and a fast mode. This should be 1 megabyte here. So the modes are defined by the size of the resistor that's available. So let's look inside here. Remember, this is the image here. You have a MOSFET, for instance, an open drain that is pulling this down, pulling this data down. And so if you want to send a 1, you put this MOSFET into high impedance mode. And if you want to drive a 1, you put it, you open it, you put it into low impedance mode, which drives this thing down and drives some current in there. And that way, you can have as many peripherals on there, and they can all share the bus. You can transmit and receive on that one data line without worrying that there's bus conditions, contention where 2 devices are trying to drive at the same time. That could cause problems if somebody's trying to drive a high and another chip is trying to drive a low. That's a lot of current that's going to get sunk, and it's likely that you'll burn something up. So let's just take a little look at this. Here's a little Falstad simulation. I've just made a very simple little drive circuit here. So here's a logical 1. You can input data in here, and it's going to turn this little inverter inverts the signal into this PMOS. That's not important. what's important is that when I drive this low, we see that the data line goes low, right? We can actually see the current flowing in through here, okay? And this is causing this line to go low. And then if I put that high, you can see it turn green again, right? So this is being the highest voltage here, and it's pulled itself back up. And so by toggling this bit, I can send data along the bus, and you can see the bit lines are going high and low and high and low. Okay. Now I say I have another device on here. I have a second peripheral, and it wants to talk. Right. So all it has to do, as long as the bus is free, nothing is touching it, nothing pulling it down, this guy can also talk. So now he's sending data. You could say he's sending data back over here. You can send it to any other device. It doesn't matter. Now, the problem occurs here. So this, when, say, this guy's low and holding it low, so he's trying to sabotage everything. This other guy is trying as hard as he can to go high and low, but the bus isn't going up and down. It's because this one is hogging the bus and driving it low. So a lot of the arbitration and things we have to get around in this protocol are around this issue, okay? So that you don't want one device hogging the bus. Okay, so all right. So just to drive home, the next comment I want to kind of get your head around is why we need resistors of different sizes, because I can change this in this simple simulation to whatever I want and get nice square waves. So let's add a capacitor in here, okay? And if I drive this low, you can see it went low very quickly, right? Because I'm just dumping as much current as I can through this. But when I want to drive it high, it takes a little bit of time, right? You get a little RC charge because I have to, limited amount of current is going to flow through this capacitor to charge it up. So let's take a look at that again. Drive it low, and then, oh, it takes a little bit of current to drive this up, and we see this goes high, okay? Now, why this is important is this is the real limitation of an I2C bus. It's its ability, it's how much capacitance on it. That's what's limiting speed. So we can see here, if I go fast, right, you can see, I'm trying to go fast, you can see that, look at all these corrupted data bits. Some of these didn't all go all the way up to the top, right? So I was trying to drive data as fast as I could in this bus, and bad things happen. In fact, we can even exaggerate a little bit and just go, let's just make it 10. Oops, that's, all right. So here we can try it again. All right, so this would be a very exaggerated condition here, and it takes a long time for it to charge up. So if I go too quickly, right, not getting any data through. Let's make this one a beefier resistor. Ability to drive more current. Now, unlikely value, but for demonstration purposes, look, we can go up much higher, right? Much faster. Let's go much, much faster. Again, completely unrealistic values. All right, there we go. Up, down, up, down. All right. In fact, we even see some errors because the resistance is so low and there's some real source resistance here. Most likely this is going to be nanofarads or picofarads. But anyways, it's important to realize that capacitance is what's slowing you down, and you need smaller and smaller resistors which can drive more and more current if you want to go faster. All right. Back to here. So what we just saw is you can have one or multiple peripherals and a controller on a bus, and each one of them has the ability to pull that line down and raise it back up, let it go back up to encode data. Okay. The controller is the only device that sends the clock. That's the only one that sends the clock. And again, it's just pulling down with the open resistor, open drain. It's either pulling the line down or letting the resistor pull it back up. Okay, so let's look at some of the timing that occurs here. So here we have the data line, the SD SDA data line, and we have the clock line, SCL. Okay. There is a very specific start condition, and that's because we have to signal to all the devices that we want to make sure people or other devices listening aren't confusing what's going on with other traffic that could be happening. So the start bit is a very specific sequence. Both SDA and SCL have to be high. Then data is pulled low for that device, typically the controller, to take control over the bus. It's instantiating that it is the one that's in control. Okay? Then clock will start toggling and you can transfer data. Likewise, there's a stop condition where clock has to go high for a while and then SDA goes high. And this is just showing, and this has to be a longer timeout than one of these bits would be. There has to be a timeout condition, and that's signaling that the bus transaction is over. Okay? So we have start and stop bits. Yeah. Okay. This is a wire and situation where you get multiple devices pulling down. So there has to be some ability to do arbitration here. So if there's a single controller, arbitration really isn't needed. Arbitration is the protocol, the mechanisms that we use to decide who goes first and who goes when. So if there's just one controller, it's always in control. It's the thing that's pulling down the data line. It's the thing that's toggling clock. But there are conditions where you could have multiple controllers. And if you're going to do that, what's going to happen is the controller is going to pull down SD data line, okay? And it has to check. It has to check to see if the data that it's doing is what it actually sent, what it actually meant to do, right? So if it pulls SD data line down and clock starts to go, and it meant to send a 1 here, but it's held high, then it's that control, whichever of the control, oh, okay, sorry. SDA gets pulled down low and it should have been high. That's the controller should see, oh, there is some problem, right? Something is misbehaving. It's probably another controller out there that's taking control of the line. It has to back off under that condition, okay? And likewise, if two controllers are sending out a stop or start condition, whichever one detects that SDA is low occurs first, has to back off. Okay, so even if you were first and you detected it, if you detected going low and you didn't mean it, then you have to give up control of that the bus to the other controller. In some ways, as an edge condition, you rarely have multiple controllers, but it does happen. Okay, so let's look. Let's look at the data packet again. Actually, let's go back up here. There is one thing I forgot to mention a little bit, and that is the clocking here is particularly weird. The controller setting out the clock, but this isn't necessarily rising edge or falling edge. Right? In fact, the clock is happening fully inside. The rising edge and falling edge happens fully inside the data bit. Normally, we're used to seeing clock happens here, and then falling edge here, and then like the transitions right in the middle. This is a level-sensitive transition inside here. So here, what's happening? It has to be on the rising edge, or on the flat part here. This is where the data is clocked in, and this is where the data clocked in. So it's a somewhat unique physical layer. We call it the phi layer, because this is what the physical layer is going to be doing. This is what the actual signal, as you'd see on the oscilloscope, are doing. Okay. Anyways, let's see. Clock gets pulled, or data gets pulled low. Then some period to start a sequence. Then clock goes low, goes high, does its normal clock things while data is getting set up. So here's the setup period, and then clock is held high, and that's when data is locked into the peripheral. All right. All right, let's look at what some data frames look like. because they're also a little interesting. So here's start bit. We see data is being clocked out, and this is what we call the command. The first part of the packet is, or sorry, the address, or the control block. So here's the address, in this case, 7-bit address. And then the controller here is saying whether this is a read or a write. So it should be W bar is what you'll often see, that meaning that a write is low while a read is high. So they're saying in this address, the next thing I send, so there's a data packet over here. This is the data packet. So here we say this address, so that peripheral over there, I'm going to write, let's say, some data in there. So if I put a 0 in, that would be a write. And I'll write the following packet of data into you. Or it could be, I want to read data out, and then it's the peripheral's job to send data out. Okay? So here, we're going to decide if we're read or write. Then we get an ACK signal. Now, this is interesting because they actually provide some flow control, which is pretty cool. Here we go. ACKs and NACKs. So flow control here is an ACK is an acknowledgement that the peripheral has indeed received the message, which is pretty cool. Because you didn't have to send, as long as you send the right address, you're going to get some confirmation on the oscilloscope or logic analyzer that this thing responded, as long as it's powered up and working. So what will happen is, say the controller is going to send some data along, say it's going to do a write, it's going to write some data into the peripheral, and here the peripheral is going to respond with an ACK. It's going to get pulled low, yes, I did receive this data, and I agree, okay? Then the data packet, so this is the address packet, then the data packet comes through, and whatever this is, 8 bits of data are being driven into the peripheral. And the peripheral was going to ACK or NACK. I mean, you could always NACK. ACK meaning that the peripheral acknowledges it got the data. The data's, it doesn't mean its data is correct, but it actually got all the data bits, let's say. I wasn't confused. A NACK means it didn't receive the data, or the data was so horribly corrupt that it could not receive the data. It's not a statement that the controller figured out that was meaningless data, or that it meant something in particular. It's just saying that I got the data. Okay, so a NACK says I didn't get it. Now, what's tricky and confusing about NACKs is if you have nothing on your peripheral bus, right? You didn't even solder anything on there, and you go tell your controller, go out there and send address stated to this address, you're going to get a NACK. No worries, you will get that NACK. Why will you get that NACK? Because a NACK is just the peripheral not pulling it low. So sometimes you can confuse yourself by saying, oh, there should be a NACK there when the peripheral's not on. So getting that ACK is always a really nice sign of life, because the peripheral is actually on trying to do something for you. All right. The data frame, yes, read and write frame and address frame or control frame. All right, control frame here, data frame here. So let's just look at a real world signal here. These are, we kind of saw that when we added the capacitor, we saw this charge-discharge cycle happening before, and you see it in the real world too. And these aren't unreasonable. I mean, you don't have to get nice, really square edges up the top. You got to get them over the threshold. This is the clock signals here. You wouldn't want little runt pulses that don't go all the way up. Like this one here is concerning. Was this supposed to go high? Was it supposed to go low? I don't know. So that would give you a little bit of suspect, but in this case, it's underneath the threshold, so it's been called a logic 0. All right, so let's kind of walk through this waveform. We've got our start indicator. That start indicator went low before clock went low. Okay, clock goes low for a while. I don't know if I don't remember if there's a very specific time that this has to happen. Usually it's device specific, who knows. But it's low for some period of time. Then we start throwing up our clock edges, right? So remember, these are inside the actual data edges, okay? So here we go, 1, 2, 3, 4, 5, 6, 7, 8. And then the 9th for the ACK. So here we go. We're getting 1, 0, 0. So this is the data line, right? So here's data's up high while 1 is going high. So it's 1, 0, 0, 1, 0, 0, 0, 1. It's 0, therefore it's right. And then we get an ACK. The peripheral has pulled this low. So now we're trying to write data into the peripheral. Next, what do we write in there? All zeros. Big whoop. Okay, all zeros went in, but the peripheral still ACKed. Okay, got it. You see the stop bit occurs, so clock went high, stop went on. Now we restart the next round. Start goes low, then clock goes low. We're going to throw in, what is this? Is this the same address? Same address here. We're going to say the same address. We're going to do a read. We're going to read data out of that address. This is denoted as 1, and the peripheral act. So it says, yes, I agree with you. You know it's a positive affirmation because it actually pulled low, it didn't leave it high. Here, so this is the address frame. Now the control frame comes through. Or sorry, the address frame. Here's the data frame. Now this is sent by the peripheral, right? The peripheral is the one that's now in charge. Right? Before, when data was sent out, it was a write. The controller was pushing out all zeros. Now it is, even though the controller sent the address, the peripheral is taking control of the bus and is pulling this thing up and down, up and down. So the peripheral went out and read 0001, 0011, and NACT, saying that it is done. Okay? It is done with that value. It has done what it's supposed to do. All right, and then there's a stop bit, and then clock went high, and then there's a stop bit. All right, so walk through of that. Lastly, we're almost to the end here. Thinking about I2C or I2C buses on the STM32L4. Contains 4 I2C modules, all with different speed modes available to it and different addressing sizes. Nice that it has, this is a multi-controller. It has built-in multi-controller collision detection. You'd have to set up some interrupts for that to handle that, I believe, or some control registers. It has hardware packet error correction checking, which is nice in the sense that it automatically checks and generates and its own ACK control, so you don't have to do that. It also has 4 interrupts because there's 4 modules, therefore there's an interrupt or an IRQ signal for each one of the modules. All right, so back to I2C, or pros and cons. So pros, easy wiring, right? Also from a chip manufacturer point of view, it's cheap, lower gate count, okay. Small, slightly smaller dies, yes, but also importantly, only 2 pins. So you don't lose that much. Only 2 wires, only 2 pins, plus ground, of course. Super widely supported. Super widely supported. Almost all manufacturers support it in some way or another. Cons, open collector bus makes debugging hard. You know, I've been doing this for a long time, and you know, I just know when I'm pulling up an I2C bus for the first time that, you know, I'm gonna have to spend a little time just to make sure it works. It rarely happens perfectly the first time. Usually you get an address wrong, or speeds are wrong, or you forgot to put solder on the pull-up resistors or something. There's always a little bug that has to be overcome, and it's hard. Sometimes it's hard to track them all down. There is another con is the speed power trade-off. You know, you have this pull-up resistor, and if you want to go faster, you actually have, you can't just drive, it's not like the CMOS outputs, you actually have to put a different resistor on there, and it, you know, it burns more power. Also, speed is defined by the hardware. With SPI, you can just change the speed on the fly. One peripheral could be at one speed, another peripheral could be a whole different speed. No worries, you just change it on the fly. Here, you're defined by hardware what it is. Now, you could always go the fastest as possible. Again, you have the power problem. Then you have the power problem. But at least, here, typically what you do is you pick a setting like fast or medium or standard or whatever, and you just go with it, and you're stuck with it if you have to go faster. It says no hardware arbitration. It does depend on which module you use and how you set it up. Look through the STM module. Certainly for the, there are abilities to do hardware arbitration, but usually it's interrupt based, so make sure you look into that. All right. Let's just do a little summary here. So by now you've probably looked through all three of these modules, including the overview, and it's good just to kind of think about the trade-offs between these. So UART, 2 wires, kilobits of tens of kilobits of speed, asynchronous, but the topology is typically 1-to-1. Still used all the time, especially if you're trying to get a signal off the board. This UART is typically used because you're going to go to a USB bridge, a Bluetooth bridge, some bridge. Okay. SPI is clocked, it's synchronous, good speed, so tens of megabits. The wiring is worse than the other two, right? So 3 plus N being the number of chip selects you get. Arbitration is done through a select wire, chip select wire, and the complexity is not that bad. I2C, less wires, medium speed, clock signal, so it's not asynchronous, it's synchronous. You got packet headers for arbitration. It does support multiple controller topologies, but the complexity is often higher, right? At least in the configuration, getting up and running page point of view, getting all the debugging doing, even though the complexity of implementing from the hardware point of view is easy, it's actually debugging it the first time is a bit higher. All right, so we don't have a grade scope for this module, which is fine, but I wanted you to think about what other kind of interfaces could there be? How about a one-wire interface? What would that look like? Right? How would you design or even think about a one-wire interface? So take a second for yourself. Think about for a one-wire interface. Clearly we know what wire is, right? It's one wire, that's by definition. But what do we think about for speed, timing, arbitration, topology, complexity? Take a minute, think about that, maybe take a few notes, and then we'll talk about that. All right, I assume we've unpaused successfully by now, and now we're together. There actually is a protocol called one wire. It's kind of amazing. It's developed as a communication bus plus kind of energy harvesting bus. So you not only do you send data over it in bidirectional data, but you also send power over the bus. And it was developed by Dallas Semiconductors, and there must have been some super weird conditions where they really wanted to get this one. So one wire, as you expect, speeds slow. All right, tens of kilobits per second. Timing would have to be asynchronous, right? If it's one wire, there's no data, or there's no clock at all. You'd probably be best to go here and borrow from, if you need arbitration, unless you're going to do one-to-one, packet headers are the right way to go. And this happens to be an N-to-1 technology, right? So multiple, one controller talking to multiple peripherals. And the complexity here, at least getting it working, is pretty easy. So the way this works is that it's just like I2C, except it's I2C plus UART, in the sense that you have to use remember in UART, you had the start bit where it was always a defined line, and you had to oversample the start bit and figure out where the middle was, and then use that for the rest of the timing. So the controller, the receiving and transmitting hardware is harder, but you only need one wire. So let's see, you have a port to control. This is an open drain topology as well. Multiple devices through multiple peripherals through one wire with a pull-up resistor. And what's interesting is that the one wire comes in through, have this voltage harvester. So if nothing's going on, current is going to go through here and charge up this capacitor through this diode. Remember, a diode is like a one-way valve. So if the voltage here is 0.3 volts higher than the voltage here, and current will flow and charge this thing up, that could be enough power, and it's not a lot of current, or it's not a lot of capacitance, but you only need a few microfarads to power something short for a brief period of time. So you charge this thing up, then it's on, it sends out maybe a couple of pulses to say, hey, I'm here, I'm alive, and then you talk back and forth over one wire. There you go. All right, so with that, it's just an example of another type that's not you will not see that in this class, but just to get you guys to think about other types of bus constructions and mechanisms. And with that, I'll end it, and the next module or sets of modules we're going to work on is I2C. All right, thanks.